impedance, as a lot of you understand. And first of all, I'd like to explain why it's so. For the last years, I've been dealing with a subject which relates immediately to general relativity. And on the same conference, Finsler extensions of Relativity Theory in Cairo in 2006, I suggested a program. I formulated a kind of program which I was going to perform, and this is one of the stages of this program. This year, I've just finished a book which is going to appear in October 2011 in the World Scientific Publishing House, where all the results that I obtained during all these years are given. And when I had a correspondence with the publishing house about this book, I wrote them the contents, the table of contents, and they suggested me to introduce a new chapter into it, which would present a state of art in the subject. Obviously, I had no need to do all the technical job. There are thousands of books which discuss general relativity and all the topics corresponding to it. But I had to have, so to say, an ideological review of what has been done before and why this new topic has to appear. The title of it is Introduction to the Anisotropic Geometrodynamics. And this Anisotropic Geometrodynamics, or AGD, it's very convenient to call it in this way, was the topic of what I was presenting for these years. More than a dozen presentations. So today, I'm not going to explain the results of the book, but I want to show when the book was written and when they asked me to make this introductory part, or the state of art, I suddenly, already after finishing the book, I suddenly realized that there is a certain parallelism in the situations which was 100 years ago and the situations we have today. Amazingly, I understood that what I had been doing was just in parallel to what was done 100 years ago. I didn't think about it myself, so this title, how impudent it is, appeared to be natural. So, in this talk, I'm going to compare. The talk has a more methodological, so to say, aura than quantitative or giving some new results. I want just to show the place of this new approach and this insights. It was based on the undetectable ether. Nobody even thought that there was no ether. It was out of the question. But when the situation with microsomol experiment took place, they had to think about it. Nowadays, the main theory is Einstein GRP. To say nothing of quantum theory, I won't touch quantum theory at all, and won't touch the quantum aspects of general relativity, only geometrical part of it. The main success of this theory is the gravitational redshift and other classical tests. And the problem which appeared was most, so to say, picturesquely given by the so-called rotation curves here, which appeared to be not as they should be. Rotation curves should fall to zero somewhere here on the periphery of the galaxy, but they did not, and they do not. For larger galaxies, we see the result, which is shown in this picture. All of these rotation curves, this is the dependence of the orbital velocity of stars on the distance from the center of the galaxy. All of these dependencies go to constant. From up, from down, but there is a constant. In order to overcome this problem, several attempts were made, and I'm going to say a few words about them. But the current mainstream is the presence of the so-called dark matter, a substance which doesn't do itself in any direction except gravitational one. And there are suggestions of what kind of particles produce this dark matter, axons or something negative to hit photons. But this I don't know anything about, and I won't also speak about it, but I want to underline the amount of this matter which is needed to make this data ether theory. The amount of dark matter is 3 or 4 times larger than the amount of visible matter. 95%? It's including dark energy. I speak now only about dark matter.
Which is even worse than
Yeah, So there is a problem with the theory. And 100 years ago, they had ether that underlined the whole thing. And now we have dark matter, which is imposed on it, which is reversed. So I will just mention a series of problems concerning this galaxy scales. The first of which I have just mentioned. This is rotation curves, which have a constant here. Also, we have Fisher law, which doesn't have any place in theory. It's an empirical law, and it relates luminosity of a galaxy to the orbital velocity of stars. For spiral galaxies, we have force power, and for elliptical galaxies, there is another relation which relates not to the orbital velocity, but the dispersion velocity in elliptical galaxies. Besides, there is a mystery about globular clusters behaving inside our own galaxy, which is also a spiral one, I mean Milky Way. The thing is that those globular clusters, we know about 150 of them. When they move in the plane orthogonal to the galaxy plane, everything is perfectly okay with them. They obey Kepler laws, and that's it. No special cases like that with the stars moving around in the plane when there is something extra. So we see that there is an anisotropic. What kind of it? This will be also discussed. Besides, this globular cluster spend that time in the center of the galaxy, not in the periphery of it. That should be according to Kepler laws. And we also have gravitational lenses. This is a whole branch of physical science and astrophysics. And the problem with them, because they think they know how to solve it. The problem with them is that the observed bending, the observed deformation of the light beam is 3, 4, 5, 6 times more than it should be according to the theory. They also say that this is dark matter and don't try to calculate the amount of it according to gravitational lens observations. So, let us go in parallel in the situations 100 years before and today. When they had this problem with Michelson-Morley experiment, what did they do? The first attempts to overcome it were ether dragging, suggested by FERT. The problem was that in this case there would be a lack of aberration which was observed. Then ballistic theory of light, riddles, but this theater, who was a famous astronomer at the time, and famous theoretician and all that, immediately pointed out that in this case we should have scrambled images of stars, double stars, which was not the case. Then there came the electromagnetic interaction, suggested by Lorentz, who was one of the leading figures of the period. And this theory was absolutely physical, absolutely according to the views of the time, and even in 1913, Lorentz was sure that his theory is better than that of Einstein, because it has a physical meaning. What do we have nowadays? As soon as there appeared a problem with the rotation curve, they started to make attempts to modernize and modify the theory. We can think about a Hilbert action expression, and the corresponding ideas were to do something with the scalar, which is standing under the integral, then to introduce more powers of R, of scalar coefficient. Another case was to introduce an additional scalar term, which kind of Browns-Dicker theory. Then there was Moffat attempts to do something with the metric tensor, and that led to the introduction of the fifth fundamental form, which you don't know about. Another key thing is to try to form a new scalar with the help of Weyl tensors. It's also okay, and these results are very profound, but all of them are insufficient to explain the observational results. Another trend was suggested by Miller, who produced an empirical modified Newton dynamics. It fitted experiment idea, but it had a couple of features which are not physical, so to say, because they are empirical. He introduced an empirical law to modify Newton, gravitational law, and he suggested an arbitrary function to be inside the expression. What to do with this arbitrary reason, we do not know. Finally, they came to the physical reason of what they saw, and this was dark matter. So, what we can say, judging by the mentioned facts, about the efforts of the scientists to overcome the problem. 100 years ago, all attempts were focused on the search for a physical reason. They thought of physics. The appearance of relativity theory made a great effort in the applying of mathematics and physics and empirical mathematical approach to physics. And that's why, at that time, before Einstein discovered, before Minkowski, it was not so clear for them how to move. And they tried to find a physical explanation. While nowadays, the case was opposite. They tried first to make some theoretical modifications. After that, they tried to do some empirical descriptions. Only after that, they were forced to introduce a physical essence, which is still undetected. So, if these situations are considered unsatisfactory, which was the case 100 years ago, and which is not the case up to now, I think many people are happy with that moment. I was not. But the situations can be compared in the following way. What did they do in the beginning of the 20th century? There was a postulate that speed of light is finite, and it doesn't change its motion. Why was this postulate? Why it could appear? What was the reason for it? It was experiment. And Einstein all his life underlined that physics is an experimental science. He is a physicist, so he used mathematics and enjoyed it and so forth. Then, if we understand that something is wrong with our general fundamental approach, then we have to think about experiment side of it. What and how should we measure? And it was immediately recognized, not immediately, but eventually recognized that the thing is that we have to regard processes, not objects. And that immediately led Minkowski to the suggestion of a new model of the intuitive notion of physical world we live in, of the reality. All of us knows what is the space and what is the time, but try to explain. There will be problems. We can use models, mathematical models, to deal with it, and to work with it, and to predict. And at that time, they lived in Euclidean space at that time, and Einstein was perfectly happy about this. In his famous work of 1905, he didn't pronounce a word about new geometry. It was Minkowski, who was a mathematician, who suddenly realized that the idea, the notion, should be modeled by another model. That was the case. That's how space-time appeared. And it had new non-Euclidean geometry. And it caused many consequences and invited new mathematics inside. Now, by the way, the situation at that time was not so common as we think it now. Students at school know about 4 dimensions and interval and such like things, and they speak about 4-dimensional manifold, don't even think about that this is a mathematical model. But at that time, one guy who realized the situation 4 years before Minkowski, and even about a year before Einstein, said that if we use non-Euclidean geometry, the past non-Euclidean geometry in physics would demand such tremendous efforts that it doesn't seem both insensible or correct. Not the last person in the world. And Minkowski was brave enough to say that Newton's space and absolute time must be substituted by a new unity. 4-dimensional space-time with geometry is not complete. They have to reformulate the whole physics. They did it. So, what do we have now? As we see from experiments, gravitation force is not Newton, because gravitational curves are flat. That's it. In the real world measurements, we should be very careful when thinking about what and how to measure. For example, physical space-time cannot be empty or flat. We can imagine it. We can solve problems with this help. We cannot register it by experiments. Because every person person who's performing an experiment is a material body who has mass. We can neglect this mass in some cases. But the way from the empty space to the space with bodies can lead to many places. Which is correct? Nobody knows. The way should be opposite one. We should construct a theory with mass and then neglect it and get to that space in this sense. Then we will get the things which we can check, not the other way. Besides, we have moving masses, and in this debate I'll say why should we deal with move motion also. So the question is, could there be a new model of reality with new geometry that could be helpful? So, looking at this picture, this is Hilbert-Einstein action. We see that several attempts were dealing with scalar, more accurate expression for it, or additional term, or a new expression. Something can be done with the help of geometry, for example, Moffat's attempts. But there is this term, which deals with the kind of a model we use with the intuitive notion of space and time. So this slide is probably the only one where I read something mathematical, because the essence of it was reported many times at various conferences. There are publications, so I wouldn't explain why this is that and how to derive this from that. I'll just mention it to show how it is applied and what consequences are. So, thinking about the possible new model of space and time, I should mention a couple of hints which make me just curious how to imagine it. There is an equivalence principle, and to stay with it, we should pay attention to its literal meaning. If we don't have any possibility to distinguish between inertial forces and gravitational forces, we have nothing to do but to agree that gravitation should depend on velocity, because inertial forces do depend on it. And there are cases, and I'll show it, where we cannot just pass to another reference frame. Another thing, the dependence of gravitation on velocity is, of course, well-known thing. And the higher orders of the regular expression of general relativity to find this velocity, we can find it in gravitational electromagnetic theory. They also made just a copy of what is done in electromagnetism and applied it to gravitation. But they had made an essential mistake, though the results are okay. Now we have experimental data which fits them within 10-15%. 10-15% is not bad. But several theorists can explain the same results, so it's not a problem of 10-15%. Geometry also uses the idea of anisotropic and of motion, but it is not also unsatisfactory when we pass to galaxy scales. Another hint is Maxwell identities. In mathematics, I guess most people here are mathematicians, so mathematicians call Maxwell equation something else than physicists do. For a mathematician, Maxwell equation, or Maxwell identity if you like, is just a sum of three terms. Take a tensor, antisymmetric tensor of specific form, just make several manipulations and get an identity. That's Maxwell identity, Maxwell equation. After that, I can just change notations and get what we know as Maxwell equations in physics. What is the meaning of these letters? Who cares? And they didn't care. Maxwell himself tried to use the technique for describing the gravitation. He failed because he had some problems with energy and with the single sign of charge in gravitation. But, for example, in gravitational electromagnetism, they use it successfully. And this gravitational electromagnetic theory is based on lense and theory approach. It's okay. So the structure, the mathematical structure of Maxwell identity is such that can be applied both to gravitation and to electromagnetism, and this is not a secret for more than 100 years. The only thing is how to do this. And the answer is, since the gravitational force must depend on velocity in an inherent manner, we have to get it directly. And this means since gravitational force is related to a metric, the metric will immediately become anisotropic. Anisotropic metric means anisotropic space, and that's it. Here we come to anisotropic space, to Finsler geometry, to Lagrangian geometry, to whatever. So I did the simplest case. Here is Minkowski metric, and here is its small deformation, anisotropic deformation. In the same sense that Einstein did in his paper, in his paper of 1916, with general relativity, but there the dependence was all on x. Here it's x and y. Y is this thing, this is a small feature, and we pass from regular, I wouldn't even call it space-time, four-dimensional space like this, with non-Euclidean geometry, Minkowski geometry for example, to this. And the receipt of constructing is this. When we pass to physical variables, we get Ct, we get V, and we get new constant, H. In the very same manner, they pass to physical variables when they pass from anisotropic space, which Minkowski dealt with before he started doing relativity, to physical space, where they appear C. Why C is the speed of light? The only reason is because it fitted the experiment ideally. Because we had to preserve Maxwell's theory of electromagnetism. It would be just velocity.
Then it is in vacuum, which is meaningless.
Yeah. Vacuum is enough. Let's not speak of million. The only thing we need is the constant with the dimensionality of speed. Which speed is it? Nobody knows. For us, it's convenient to have speed of light.
Yeah.
Here, when we pass in this way to another space, we also have to introduce a new constant. It is dimensional constant because we have different procedures of measuring. That's why we have to have a constant of special dimensionality.
Has to do with the quantum cutoff H?
Huh?
Has to do with the quantum cutoff H?
No.
No. It's just a geometrical fundamental constant.
These two are just two geometrical constants. Nobody knows which.
Since you're doubling variables.
Huh?
You're doubling variables.
Yeah.
So you have a further constant.
Sorry?
You have a further constant since you're doubling the variables.
Yeah. So in this case, the geodesics should be generalized to this form, and we have a new term. And when we start...
Sorry, is it covariant? Is it covariant?
It is. And when we start to use the approximation using this approximation, we immediately come to such expression. And this is just the case of Einstein, who reduced... I just followed his work, step by step. The only difference is that he had no anisotropic, and I did. And here is a new term. With the help of this term, we can get a new expression for a dynamical equation, or an expression for gravity force. We see that this is the Newtonian term, and this two are new. The curl term which you have here can be also met in the usual general relativity. But here, the difference is that it has 0, 0 indices. They are not space but time. So that's why this term is not cannot be excluded with the path transferred to another reference frame. And so I won't talk anymore about this approach and mathematics because I did it many times already. What I want to do now is to follow this parallel steps. But I have to mention the results because that's the reason why should I do this discussion of parallel steps should be somehow grounded. And it can be grounded to my mind by the following results. First of all, when we come to this new understanding of gravitational force, we have to realize that the previous model of the gravitational source, which is a point, is not enough. The point does not resemble, does not give an idea of motion, of an isotropic thing, of the effect of moving parts on the other, same method. So there must be something moving inside. And we have a very nice picture of it like this. In electrodynamics, it's absolutely clear, but you can use it in gravitation as well because of the same roots of the mathematical structure, because of the same Maxwell identities. If this is a charge, and this is another charge moving around, actually it's a current, then this whole object is an elementary source of gravitation in this new approach, because it has a moving part. It's solenoidal. By the way, from a mathematical point of view, it has a solenoidal part. So it's clear how to apply this model to describe objects like these. These are evidently rotating circles or something like this. This is the simple rules how to transfer observations to theoretical values. And these are the results. As soon as we start to use the new expressions for gravitational force, we immediately have this answer to rotation curves. We have two roots of the simple equation. One of them is 0, as it should be, according to Newton, Einstein, Schwarzschild. Another one is constant. Here is this constant. If we try to calculate it, we'll immediately find out the reason for the choice of Milgram in his Mond theory, who paid attention to the fact that they needed a new key, needed a new constant, empirical one. And that empirical constant was very close to c times h, where c is speed of light and h is Hubble parameter. The Hubble parameter, by the way, has just the very dimensionality we need as this new fundamental constant I mentioned. So if we take new parameters, these fundamental parameters of the new theory as speed of light and Hubble constant, we immediately get this constant which has the needed value according to observations. Also, when we try to calculate it, we also have Tully-Fisher rule in a very simple manner. And also the problem of globular cluster dynamics is also becomes clear because there is an anisotropy which is caused by rotation matter in galaxy. And the new terms which we had in the expression for the force here depend on the direction of this velocity. So this problem seems to be solved. Now we have to check what happens to the so-called classical tests which Einstein produced. Now we have new model, so we have to check if it works. So in this picture it is shown the two trajectories. Oops. This trajectory is a light bending on the Keplerian, so to say, Newtonian center, on the point gravitational source. Now I add an effective mass current around it and let light pass near it. We see that the bending is larger. And if this source is a gravitational lens, I don't see any reason to introduce dark matter. In a similar way, as I have no reason to introduce dark matter here. It's just motion. Make a little step explaining gravitational lenses and get some formulas. This is a formula known nowadays which deals with the gravitational lens and the so-called Wilson-Einstein radius. Here it is. When we have a galaxy, a spiral galaxy, which is oriented like this, and the source is situated here, and the light beams are going this way, there will be a kind of radius which was calculated by Wilson and Einstein, which have the following expression. But if the galaxy is oriented in this way, then we see that the picture turns to be asymmetric. We're going to get the expression for this analogs to Wilson-Einstein radii, like this. And we can try to apply it to the known models, to the known objects. For example, Einstein cross. On this picture we have an image of quasar, which has 4 images. It's one and the same quasar, which is situated here. seems that the picture is not very bright, because on this picture there is a picture of a galaxy which is a lens to this one. Here, on the third picture, these lines correspond to the orientation and the position and the location of the bar of this spiral galaxy. So you can have some. So do you see this galaxy, which is like this? Unfortunately, it's through the light is too strong. So if you apply the formula that was presented on the previous slide, we see that the ratio of these two segments is awarded 10 in the 0th power, which is in accord with observations. It can hardly be used for anything because we don't know the exact values for these distances between the observer, the lens, and the source of light. But it means that this type of asymmetry finds its explanation inside this new approach. No doubt in it. Besides, we have an extra bonus. If the source is located close to the possible gravitational lens, which has this anisotropic feature, then we see that the light can have two bendings. And in this case, this lens became concave and not convex, as it usually is. All those who have spectacles like mine can understand what does it mean. We see images that are smaller than the sources really are. But then how to interpret the famous information about supernova of type 1A, which breaks the Hubble, the linear Hubble law. It could be just because the interpretation of what we see, dealing with their dimensions and their luminosity, if it happens that some of them, at least some of them, were regarded within such kind of gravitational lenses that would be met by the light beam of the Earth, then we should evaluate the distance of the source in a wrong manner, and this will cause just to the same results as we do have when speaking about the acceleration of the universe expansion. Maybe no acceleration is needed. So when you just mentioned the dark energy, we see that from this point of view, there could be no dark energy. Finally, a very picturesque, not finally, but still, I like this picture very much because I struggled with it a lot. So this is a calculation of the following situation. There is a center of a spiral galaxy which suddenly explodes into two pieces, not into two pieces. There is a burst during which two parts of matter go in the opposite direction with the same velocities and they have approximately the same mass. So let's calculate what will happen. And here is the result. When I got it, I was very happy about these angles because I knew a lot of images like this produced by Hubble and other telescopes and observatories. But I was very unhappy with this, especially when I found out that it depended on the step of calculation. When I changed the step, it was numerical result. When I changed the step, these features started to change. Not essentially, but still. They turned a little bit, they became larger, smaller, but they were always present. I thought it was some defect of some numerical procedure, something like this, but what could I do? But then I paid attention that there is a similar kind of thing on this picture, for example. A couple of months ago, there came new information which was sent to me by Alexander Lavshen, thank you very much, in which there was mentioned that the Herschel Observatory produced several images of the center of our galaxy where they found the following. This band, you can see that there is a kind of band, but the band itself was drawn by the interpreters. Actually, the data do not give any band. It can just be interpreted with the help of this band. But the maxima resemble, the maximum distribution, resemble this figure of infinity. You can find it. It's a nice trick. I don't know how it happened, but it happened. So, another test of the classical test is the orbit precession, and naturally it is present because as soon as you deform the Newton law, you start having precession, and we deform it. So there is a precession of stars and galaxies. By the way, I forgot to mention that why this is also important, not only beautiful, but important too, because there is a theory. Nowadays we have a theory of the origination of galaxies' arms. These are some density waves, and I read this article. Mathematically it's very beautiful, but with the help of this approach, we cannot explain how do bars originate. 2/3 of spiral galaxies have bars. The density wave theory doesn't give any answer about the bars. Here we have it. So the precession is also present, which is not surprising. And here, just also only one slide about the possible experimental test of this theory. To explain known results is okay, but we have to suggest a kind of experimental test which would be characteristic just to this approach, not to something else, and which would help to explain some results which could be obtained, which are not present yet, but could be obtained. It happened so that before I started dealing with this anisotropic and anisotropic geometrodynamics, I dealt with the problem of calculating and probably even observing the gravitational waves emitted by the periodical gravitational waves, not catastrophic ones as they usually look for with the help of those detectors and telescopes and whatever, and the LISA project which is going to be launched in several years. It turned out that if the source is periodic one, the source of gravitational waves, for example, it's a closed binary star system, very close. The shortest period we know is 5 minutes. Imagine two stars rotating one around the other, one cycle per 5 minutes. Extraordinary. And we have about dozens of such objects. So there was a theory which predicted the existence of the so-called optical metrical parametric resonance, which predicted a signal which could be observed while regular observations of cosmic masses, radio sources, which are frequent in the universe. And a couple of years ago, we started the observations in Pushkin Observatory, and we managed to find these are the first promising results that we have. I mean, that the signal, we already see the signal. The thing is, what ability does it have to the anisotropic geometrodynamics I speak about? If we have enough statistics of such sources of gravitational radiation distributed all over our galaxy, we can try to compare the results, the theoretical and experimental results, which correspond to the location of the system of maser and double system in the plane of the galaxy and in the orthogonal plane. There will be difference. According to the theory, there should be difference between these two signals. And we can compare it. And we can get information about the anisotropic of Milky Way. So these are the first steps. As soon as there would be something like 100 observations, we could make some statistics. So it seems to me that there are grounds to think about HB as a theory that can predict, can be capable of predicting, and has a right to exist, and so forth. So that's why I try to have some parallelism between the situation 100 years ago and the situation now. So the continuation. It's not the end of the story, by the way. So when they had a new model, they and Einstein immediately generalized it and obtained GRT. After that, the exact solution starts to appear. As soon as mathematicians understood that there is a field for the applications of their results, they started to apply their results and their knowledge and their skills and so forth, and we got a lot, not a lot, but a set of exact solutions. Those solutions changed our worldview. and Einstein times believed in a stationary universe, no galaxies, the only one. It's only in 1923 that they realized that there are galaxies. Until then, nobody knew about it. That's why Einstein thought about cosmological constant and such like things, because it was hard to understand how does this object exist. When Friedman solution appeared, also that one, we had our cosmological picture has changed essentially. Now we have, even before this, after Schwarz's solution, we have black holes. There is a whole branch in astrophysics, black hole physics. We have universe expansion. Everyone knows that it expands. We have Big Bang. Everyone knows what Big Bang was. We have dark matter, the latest issue. We have dark energy, also one of the latest, the most latest. And looking at this, one should immediately ask, why, having so wonderful and picturesque consequences, do we have problems in explaining rotation curves, for example? All this is so beautiful. Lots of institutes are investigating why rotation curves are flat. And when we come to the suggestion to explain all these things without dark matter and dark objects and whatever, let's have a look. What kind of mathematics we need now? Here we all are geometrists, so it can be helpful, guys. So we have a new model of reality. We have a consequence, for example, this approach, which I call AGD, but probably it's not the best variant, and not the best variant of this theory. The question is, what kind of mathematical aspects are inherent to phase space-time? What kind of mathematics it involves? And what kind of cosmological consequences does it presume? Here, we really have to have a trouble. Exact solutions are not so good as we used to think. For example, if you try to think if anything is wrong with them, we immediately come to several questions to think about. Here they are written, so I won't just read them. But I would like to give an example of possible inconsistencies in what we know very well from the very beginning, for example, black holes. So, let us regard a homogeneous spherical body with radius R0, and let us pose an internal problem, not an external one, like it was for Schwarz, but an internal one. Find the solution and demand that the solution from inside the internal problem coincide with the external solution. It's very natural. We'll immediately find the following. So this is the solution of internal problem, Schwarz's problem. And we can check that as soon as the radius of the sphere is 9/8 of the radius of the corresponding Schwarz's radius, the time stops and changes sign. For example, if it is a gravitational collapse, and the collapsing matter reaches the value of 9/8 of Schwarz's radius, before just becoming a black hole, it is just above the horizon. But starting from this point, there is repulsion instead of attraction.
Yeah, because it is not rotating.
For example, because it is not. But
it is unphysical because it's not rotating.
The question, what is physical, starts to be entertaining and curious. What is physical and what is not? From the point of view of black hole theory, of course. But
it's what you see. There is no star which is not rotating.
Okay. Nevertheless, I don't like this. I don't like the situation when something becomes like this. For example, I can imagine not rotating. So why not? Let it be not physical, but still. And this is the inconsistency. For example, if we think about the universe as a whole, if we think about the universe as a whole and calculate its Schwarz's radius, we will immediately find out that it is equal to the radius of the visible universe. Where do we live? Inside or outside? What kind of solution should we apply to the description of the world around? So the exact solutions should be checked. Now a couple of words about the mathematics that can be involved because of this new theory appearance. Since we transfer from three-dimensional space-time to n-dimensional space-time, we immediately see that this new object can be represented, can have a lot of subspaces, which are very famous to us. For example, this is just a space-time, these coordinates. These coordinates is a well-known 6D space-time of general physics, and we use it for years. And nobody cares about high dimensionality. It's not the dimensionality in Kaluza-Klein theory, where they are conventional. Here it's just a regular thing, just to describe, not to have some meaning of coordinates. Here we have the theta space, which is a good model, maybe better than Einstein's. By the way, in the time of, in these early 20s of the 19th theory, the theta was the leader of explanation of the universe, because he was a strong new things. And Hubble referred to the theta's model, not to Einstein's. So it is useful. For example, if you take this set of coordinates, we immediately get the relativistic velocities theory, particle theory, Lobachevsky geometry inside. Works perfectly. So we know pieces of the whole picture. And these pieces are investigated very well. Why not combine them? Lawrence, I haven't talked about these sentences, but probably I have no time, and I'm sure we can discuss it later. But the thing is that we have to do away with the ideas of not only way to space, empty space, but of regular Lorentz transformation. It should be generalized. For example, in this way. And here we have a new parameter, and this parameter is related to the parameter of ADD. So we have to bear in mind that it is known and shown that it's not the Poincare group that is the most general, it's the theta group. And the theta group has an important property. It can be contracted to Newton-Hooke group. And Newton-Hooke group is ideal for astronomy and probably good for quantum mechanics.
Yeah, exactly. It's the same.
Yeah.
That's why I was saying it before.
Okay.
There has to be rotation somewhere. And the universe cannot be asymptotically flat. Cannot be.
Yeah, right. Absolutely, I agree. We have to think about boundary conditions. The regular idea about flat space around somewhere in infinity is wrong, because we cannot check it. It's a mathematical problem which has a solution. It's not a physical problem that can be checked. Instead, we have to regard a problem with lacing between external problem and internal problem. And this lacing is just a geodetical motion. This motion we can check observing the bodies. Looking at all this, we see what kinds of new mathematics should be introduced. For example, from the geometry point of view, we have to think about jet space. Because the step I have made is just the first one. The next one are coming. So that's it. And finally, I should mention the cosmological consequences, and this will be the end. Of all those mentioned GRT consequences, Big Bang still seems inevitable. And this has a strong thermodynamical background. It is well discussed by Penrose and other people who understand what it's all about. And it is very well backed up by observations. Very accurate observations, according to which we think that Big Bang should have been. But all the other features have alternatives. The same data can be explained by various reasons, for example, by the theory like this. And then we see that we have no need of pragmatic cosmology. Hubble linear law can mean not only expansion, radial one, but also tangential motions, not rotation, but tangential motion in various directions, like in a turbulent world. The model for the universe is turbulent flow with all those worlds for galaxies or such like places. Then we have to check about this as a 1A situation, whether it is real acceleration or whether it can be explained by the lensing, which becomes anisotropic and therefore not the same. Finally, we have a theory for rounds and barns, which is not bad as a bonus. And here is the observation which show that in the periphery we really have very fast moving objects that can affect the situation inside. So this is just the repetition of what I have said, and thank you.
Thank you. Sergey, we have a couple minutes for comments and questions. Peter?
How does this square with the critical density concept? How do you square this with the critical density concept?
Critical density concept relates very closely to the dimension of the universe. We have to define what it is as soon as we do it. By the way, it's just how to say it, just squeezy thing. All this density, dimension, how do we evaluate all these things? It's place for discussion. There will be something like this. And by the way, these are the first ideas, and I have no just far-going statements. We have to think about this in this way also. All these questions should be answered for us.
Other comments or questions? Yes.
Well, first of all, I have a general comment. I like very much this approach because it is clear now that the paradigms, both physical and mathematical paradigms of Einstein relativity theory, are not enough. Definitely, because of a number of reasons that you mentioned, many of them, but not all of them. And so it is definitely clear that has to be changed in a number of things, among which, for example, the geometrical structure one is looking at space-time, and the physical interpretation of the constants and of the objects one is looking at, and the physical and geometrical interpretation of the data, which are seen now that were not seen at the time of Einstein. But I have a comment. When you say it, I'm not saying that it is not a good approach. It's a very interesting approach, this approach of having a space with a number of extra dimensions, which in fact are hidden, because in a sense you're using the tangent bundle rather than using the manifold itself. So they are there. You see 4 dimensions, but there are more that you use. So I completely agree on this. It's a very interesting part. However, when you say that among the attempts to overcome the problems with dark matter, they are all wrong, in this I do not agree. Can you go back to the second transparency you had? Okay, that one. When you say
they are
that,
not wrong.
okay,
they are insufficient.
They are not sufficient, but this is not true. This is not true. It is not known whether they are sufficient or not. It is a common attitude of physicists saying that these models that you have in that column are not sufficient because they cannot prove everything in specific examples. And if one accepts this view, which is the standard view in physics, sooner or later someone will tell that also the theory you propose is not sufficient.
Absolutely.
And this is wrong. This is a wrong attitude.
Yeah.
So I am against the wrong attitudes. In that column, there is a number of things which might be sufficient, and physicists say they are not. For example, the theories in which we are working, which is FERT theories, there is no proof that they are not sufficient. It is a common opinion. That's another story. It is a common opinion, which is wrong, because there is no proof that working with nonlinear theories of gravitation, one cannot show evidence, mathematical evidence, for the data that are seen. There is no proof. We wrote a paper on this. This does not mean, however, that this is the correct model. It's another story. It might be one of the models. And there is no proof that the models of Moffat with the non-symmetric metric are wrong. The examples do not prove everything. But there is no proof that from that theory one cannot get results. However, there are proofs that out of general relativity you cannot get everything. Because general relativity does not and will never predict a number of things, never predict a number of things as it is without changing either the gravitational content, namely Einstein equations, or the matter content, namely the stress tensor. So it is clear that the only way out of this relies on at least one of the following things: changing the mathematical structure used to describe the universe. For example, as we do, working with the metric and the connection, but it's not the only prescription. Or working with other objects more complicated, like for example scalars and non-symmetric metrics and so on. Or working with nonlinear objects which are not used.
Maybe you could continue this discussion during the break. Please.
I have to
But we're talking. Then also changing the matter content.
Look, it seems that I have produced the wrong impression. I think that nothing of what you just tell us has a negative to what I said, because I did not say that this is wrong. And by the way, take a Taylor expansion, you can approximate any function with any accuracy possible. Therefore, FERT theories are good in this sense. Which term to stop at? As to this thing, of course, any of this theory being driven to the limit will explain everything. What is the relation between the cost and the effect? And I never said that the AGD is the final theory. Of course, it's just a single step, and this is how natural science works. No absolute truth. No. Just the next step. That's it. So, I agree with what you said, but I never told this myself.
Just one comment, if I could make this comment, please. At the beginning, you said you were going to ignore quantum mechanics and quantum field theory, but that's ignoring, really, I think, the most important part of physics. And we have this outstanding problem in quantum field theory of understanding the vacuum energy density, as you know. And it's widely believed that the accelerating universe is due to the vacuum energy density. The problem is that when you calculate it in quantum field theory, even with a, maybe not so extreme cutoff, it's many, many orders of magnitude too big. And so explaining the vacuum energy density and its relation to the cosmological constant is very important. So I think it's very important that you try to incorporate considerations of quantum mechanics and quantum field theory in your theory. I'd like to thank you for your talk. It's a very nice talk. Let's finish.